system is actually a product, or it's a name of a service from a company that's now partnered with Facebook. And what they do is they take all of your identifiers and they combine them into a single ID, a real ID. So no matter how many bogus identities you come up with, they will still figure out who you really are. And they partnered with Facebook because Facebook tried to start marketing, and a lot of the companies that they were going to, market or sell marketing services to said, no, unless you can prove that there's a real ID here. They didn't trust Facebook's ID. Even though Facebook says, these people are real, they still didn't trust them. So they said, use the audience operating system, and then you can really use our marketing services. So if that makes sense, it's basically that, the reason why people don't want you to have a true ID is because they're hiding a lot of their identities. And we do this in the real world. So if you play soccer, you have a soccer identity. And if you go to your kid's picnic, well, then you have a parent ID. And so you have all these groups that you belong to, and your ID is very relative to what you're doing. Big data makes it very possible for someone to say, I know everything about you. You can't hide that ID from me. And so that makes people very afraid. So Pinterest is another interesting case where big data is being defined. The interesting, or the Pinteresting thing here, is that if you log in, every time you log in, you want everything to be fresh for you. And so Pinterest has tried to figure out a way to scale to the point that when you log in, you can see everyone you follow, everyone who's following you, everything you're looking at instantly. The way that they can do that for 70 million users is to have all that in a giant cache. And that's pretty amazing. That's a huge amount of data. And if you look at the diagram they've created, you can see it gets pretty complicated fast. All this activity you're doing has to be updated at such a huge speed that when you log in, it's always current. So the definition of big data, when you think about these 3 V's, is really more and more this. It's this real-time state of knowledge about you. And it obviously begs the question, how safe is that, right? So while I'm going through a lot of this research, I'm also thinking about my own life. And one of the things that happened was, as I was traveling through China multiple times and worried about everybody getting into my stuff, is they were actually getting into my stuff. And I tested it multiple different ways. Besides my laptop itself being tested, I can tell you a whole story about that. There were things like I would come back to my hotel room and my cables would be wrapped up nice and neat. They'd go into my bag, they'd pull the cables out, they'd wrap them, they'd literally set them back in the bag where they were, but they were nice and neat. I'm surprised they didn't put bows on them, My clothing also, not just laundry, but my dirty laundry. So I'd go back in, and sure enough, my underwear would be folded, and my socks would be. And so it began to be sort of strange, and I began to realize that surveillance is almost it's a type of service. If you have a maid, you trust that person because you've hired them, you've bonded them, you know that they're going to come into your house when you're not there and do these cleaning tasks and go through all of your stuff. Well, in China, there's almost this culture of people doing things for you, implicit, that we don't even get here. And you begin to appreciate it. You're like, well, I hope they go through my stuff and clean it, so when I come back, it's nicely folded. Which is very different than going there and being like, God, I hope they don't touch my stuff, right? So there's this weird definition thing that's very cultural around big data. People knowing things, knowing everything about you, knowing more about you than you might even know because you're not paying attention. All right, so let's look at it from a really interesting research perspective. There's a story-driven summarization of egocentric video paper that I recommend if you're interested in some weird big data research, which is if you take every data point that's coming in on the video stream, and video is going to be 60 or 70% of all data when we think of big data in the future. The vast majority of data stored is going to be video related because it's so huge. Audio is part of that also. But if you go out and you pull down all of the video from all of these, they call them egocentric video, which I think is a little harsh, but from these personal video devices, phones, GoPros, right? All these people are so into recording their babies and their latest bike ride and their walk to the store. If you download all that data and you try to figure out a cohesive story across it, you need a pretty powerful analytic engine. And so these students are working on ways to do that. And here they give 4 different methods where if you just randomly sample all the video across time, the story doesn't make any sense because a lot of the screenshots will be pavement and then tree and then what was that person doing? But they developed a method where they could actually figure out this person got up in the morning, this person went and bought this person went there, and then this person went home. And it's an algorithm that seems to work fairly effectively, and this becomes very, very interesting very, very quickly because if you realize that in 2009, the US drones themselves generated 24 years of video, you can see how some of the newer spy planes actually have so much video they can't use networks anymore. They land them and then a roving vehicle is supporting it to dump all the data and take the disks away until they figure out faster download speeds. But when you grab huge amounts of drone data, you can figure out stories for everything using these search algorithms within the big data. And this is I'm not just saying this because it's really cool and sort of futuristic, but because it's actually kind of where we're going. So how are you going to protect your story if somebody can find it using an algorithm? You don't even know what your story is. All right, so you're not really paranoid if they're really watching you, and I warned a few years ago in one of my presentations about Blue Toad. I don't know how many people heard about it or saw my presentation, but Blue Toad was the ability to monitor everywhere you go on Bluetooth. There are sensors on all the signs, so people are worried about sensors for your fast track devices or your bridge. We have fast track, other places you have other toll devices. A lot of those are on light poles and only on highways, certain parts that are toll based. But Bluetooth was being monitored everywhere. So they were putting it on stop signs. So if you get off the exit and then you go places elsewhere in town, it would actually still monitor your movements. And Bluetooth is cool too because it's not just one tag per vehicle, it's multiple MAC addresses per vehicle. So you could actually track, there are 4 people in this vehicle who have different identities, different devices. So law enforcement was buying this data off a company that was developing this huge database of Bluetooth tracking. And it's a real thing, it really works. And this is an example of how it's being used in a different way. It's Twitter. So this is called Blue Jay. Apparently blue is an indicator that it's good as opposed to white. We use white and black. The law enforcement uses blue for police. And so the attributes here that are important to me are that it's covert and invisible to you. So you're generating a huge amount of data and you have no idea that someone's looking at this. They're completely invisible. There's no way to know that they're looking at you because you're generating it and leaving a huge shadow. Second, it's browser only, so the people who are developing these tools are developing them in very fast, agile, and lightweight ways. All they need is a browser to go and start looking at this data about you. There's no like $2 million NSA nation-state echelon level of technology that's needed for your police department to be successful at this. And then third, access to your data lake. I mean, is it really yours? You're generating this huge amount of data. They call them data lakes now in big data. And so as you generate this huge amount of data, well, people can just go in and look at it, dip in, stick their foot in, see how the temperature is. So are you really paranoid if everyone's in there looking at your data that's being deposited? Video, audio, and so forth, trails, shadows, and so forth. So this to me is really the definition of big data. And in 2012, you can see we generated 6 gigabytes of new information every day. How many people believe this is true? Anybody? Yeah, so actually that's kind of a lie. So I just made that up because so many new data sources I see, and it's like I read this stuff all the time to try to keep up with it, is just mind-blowing. It's like I don't even know what that number is anymore. Zettabytes, petabytes, exabytes, and I don't even believe it at some point. I start to think, they just made that up. Like, I worked at companies where they'd say, like, we have 2 exabytes. But you didn't really count 2 exabytes. Like, you came up with that number just because you had like 5 minutes to get to the meeting, and it was like, I need a number. So I don't get too scared about volume anymore, and I think that's sort of the trend now. The big data trend is to say, hey, stop thinking about volume so much. It doesn't really matter. It's a lot. It's really a lot. So we're getting there. But if you really care, you can go around and try to hug as much data as possible, and no, that's actually, we can look at real data and we can say in 2000 there were 2 exabytes of new information. So in 1 year we were generating 2 exabytes over that period of time. And then in 2012, supposedly we generated that in every day. So it's not so much how much data we have, it's that there's an accelerating graph. It's the hockey puck of data being generated. So the more devices we have, the more sensors, the more data. So that's an example of how volume has been accelerating rapidly. And a good example of why is like, there are a lot of flights in the world. So if you say, okay, there's 60,000 routes, and there are multiple flights on every route, so every gas engine has a number of sensors that it's monitoring what's going on, and then that engine creates 1 terabyte of data, so now you have 1 terabyte of data per engine per day on all these planes, on all these routes. You just do the math and you end up with bazillions amount of data. The reason they want to know this is because they save so much time when those planes land if they already know all the things they have to fix. And they also can reduce fuel costs, and they can just know, it's like, the giant brain can take in more information about the outside world. American Airlines just released a little data point I thought that was interesting, that they removed all the paper in their cockpit, which saves them 400,000 gallons a year just by switching to iPad. So that's the sort of data analysis they're doing, is like, how much money can we save to get fares down, to improve speed, reliability, and stuff. So that's the really nice, neutral look at big data, the amount of data that we're generating. But there's a much more sensitive side of this, which is much more controversial in security, which is we're looking for a lot of clues ourselves, and we're doing a lot of data dumps. Sort of a bad pun in this photo, but People are really looking for information in places that they think they can analyze, and everybody's doing it, from the youngest child in your family with their new phone to like grandfathers and grandparents, grandmothers. So, on a more serious note, we really are measuring the output, and it's kind of scary how there's 1.5 billion gallons a day of wastewater coming out of Chicago, and so the latest research has shown that you can find all sorts of interesting things in there. You can find diseases, maybe before people know about them, right? Spread of disease, because you're looking at the waste coming into the wastewater system. You can look for drugs, and you can look for environmental risk. Lots of studies showing fish in neighborhoods are dying because of the types of drugs being put into the wastewater. And it's not like compliance, where FDA says this is an okay drug. It's actually looking at the data points itself and saying these fish are dying and these drugs are in the wastewater system, so who cares what the FDA says? This is an actual data point that shows that that's the cause. And so taking this to a level further, they can actually look at all of the drugs that are being bought in the prescription lists, because prescriptions are obviously a data source, and then they can look at all the drugs that are actually found in the wastewater, and they can say there's a mismatch. These people in these houses in this neighborhood bought these drugs, yet this was the drug that was in their waste. So they're obviously buying illegal drugs. They can actually differentiate between legal and illegal drug because they have a different DNA or data source type or footprint. So monitoring becomes pretty interesting. And so it's pretty scary at the cloud level, if you will, but if we maybe had endpoint monitoring, it might be a little safer. So it's another way of, this is an actual toilet that was designed to monitor your health. It'll print out exactly like all sorts of stuff about you. So you can do your own data point. But it's endpoint, so who knows the reliability. Wouldn't want to get a virus in there. All right, so the reason I make those points is because it's not just flight engine analysis. People actually end up seeing this and getting scared and going, I don't want people to know what drugs I'm taking based on my wastewater analysis that I have no control over. And just as a side tangent, I don't know how many people realize the Amish actually don't mind electricity, right? Does anybody know that? Amish are totally for technology, right? What they were against was being connected to something they had no control over, the cloud model itself. It goes back to the 1800s and a little bit prior to where the German philosophy, Diesel in particular, was part of this. He said, we shouldn't align ourselves with something which is out there, which is controlling us, that we have no ability to manage ourselves. So if we don't create it, then we don't use it. And so that's the Amish philosophy that got somehow transposed into we don't like light bulbs. And so there's basically a distrust that's coming back again now, where people are looking at this and going, wait, do I want to be connected up to the wastewater system? What if I have my own composter at home, my own toilet that doesn't connect up to the sewage system? What if I don't connect to the grid? And so we're seeing this already in the big data science space, where people are not only masking their footprints and taking steps. 86% of people are making sure their footprint is erasable or erased. But you're seeing data scientists themselves warning people, saying, don't put your data in here because we'll do things with it and we'll find out about you, and making a point of being like ethical researchers. So an interesting example of this is how, more and more information you know about people, you can use against them. So there are green cards that are being denied to people because they have tattoos now, because those tattoos apparently are gang symbols. And so this interesting, I don't know if you can see this interesting expert testimony of a witness on gangs was saying, U.S. officials really aren't competent to know what tattoos are gangs and not gangs, and that's expert testimony on gang tattoos. And so at the same time he's saying that, you're seeing the Biometric Center of Excellence, the BCE. I don't know if you heard of that. That's an FBI Biometric Center of Excellence. They work on a lot of fingerprint stuff. They're actually currently out, or I guess the RFI closed already, but they're out asking all the researchers in the country for databases of tattoos and their meaning and significance. And you can imagine what that's for. They're going to pump that into a system, and then they're going to try to do video analysis of tattoos, and then they're going to try to have it decide whether or not you're like a threat or not. So you can see, in a lot of cases you'd remove data, but in some cases, how are you going to remove those tattoos fast enough? Maybe you put tattoos on to look like a threat, then remove the tattoo later so you're less threatening. So all sorts of ways you have to game the system now. We also tend to poison the data intentionally. I love this tweet where this guy says, here's my idea. I'm going to totally take a picture of pulling a baby out of a spacecraft in a forest, and then I'm going to hide it in my attic so when my kid finds it later, they're going to think, oh, that's where I came from. No, this is a tendency humans have to sort of play practical jokes and poison data because we think it's funny. It happens all the time. And so another one is we torture data. I don't know if you've seen this video. How many people have seen this? No. Okay, so this is how Google Glass will be used by guys. This is kind of a silly video about a guy who gets Google Glass, goes on a date, and then he starts with these like feeds coming in, telling this woman random thing, like this is a friend of his saying like, tell her you're a beast, man, just tell her you're a beast. And he's like, what? And he brings in, she says something about like, I watched this TV show, and all of a sudden you see like Wikipedia come up, and he's like scrolling through the TV show, and then he goes to IMDb, and he's like, yeah, that actress, that one. And so he's totally like faking his knowledge about everything using Google, everything she says. It's sort of funny, but the point is that we use data to represent ourselves, and even we represent others improperly. So we use data in very strange ways. And that can create very strange and unintended consequences. It can become very scary. Like, if you look at the data in an environment like a neighborhood, you may find that, you know, all this data shows up. This comes from an old presentation I did a couple of years ago where I was making the point, you can say, okay, this person's a felon, this person's running rats, this person's bribing the government, this is all data you can pull. This person's on a trip to Kentucky, this person had a heart attack, this person is, you know, touring MP3s, and this person has 3 handguns. And we arbitrarily sometimes decide, this goes back to my political science and philosophy background, but we decide what we think is bad, you know, like, okay, we're going to look at all this data, and then we're going to say, oh, guess what I know? I know that this neighborhood has this type of bad influence. One interesting study that's been done is a guy who created the cost of a neighborhood. So you know how you look at Zillow, which is a big data example, also constantly going up and down, constant rates of neighborhood, you can look at all sorts of data. Well, this guy did the opposite. He created the map of a block and gave a value to it based on the people who'd gone to prison. So the cost of all the prisoners incarcerated from each block would show the cost of that block overall. So 5 people go to jail, cost of each person multiplied by 5, that's how much this neighborhood costs to live in. Something like that. So you can see how we can sort of assign all sorts of meaning to the data. And there are good examples of how this has been done in the past, perhaps badly. This is the FBI in 1943 when they were capturing 112 million fingerprints, files of fingerprints. So 112 million files. Anybody have any idea how many people lived in the United States in 1943? Total population? No? Any guesses? How many? No, that's close. 100 million? If you get it right, I'll give you a drink ticket. I'll give you 112 million drink tickets. No, actually, it's 80% of the population, so it's just a little bit over that, 160-some million. But still, 80% of the population of the U.S. had their fingerprints in the FBI warehouse in 1943. So it's pretty pervasive. So they're collecting all that information. And if you look back, there are a lot of bad things done with a lot of that information. Blackballing, for example, was one of the McCarthyism, all that sort of crazy stuff that was going on. So fast forward to today, we have the NSA doing a miraculously better job. So one of the interesting things I've run into is a chess grandmaster takes about 650 milliseconds to make a decision about serious risk, because they're obviously trying to figure out how not to lose a game. There's risk to their pawns, risk to their pieces. That's pretty fast. So that's considered extremely fast risk judgment. Well, microchips are operating at fractions of a millisecond. So if we're building big data systems to do risk analysis for us, to do like contextual awareness, links, remember IDs, to figure out what your real identity is in these big data systems, and then they're operating that quickly, then they should be making great decisions for us, but they're actually doing the opposite. So this is testimony recently by one of the officials on the NSA big data system who said, you know, we found out basically looking at all the phone logs just of all the pizza shops they were connected to. So you could really figure out where to go for pizza, but you couldn't really figure out who's a terrorist. So they're launching a product now called No Help, as opposed to Yelp, so you can find the best pizza places. All right, so if we fast forward to that NSA example, there's a real consequence to this, which is in our big data systems, we're finding that our society is pushed to velocity, is expressed perhaps best in the financial sector. I worked in a large trade, I was actually in charge of security for a very large trading company. And so we had super fast system requirements, and the latest data, this is long after I've left that company, but are showing that mobs of ultra-fast robots, this is a quote I really like, it's from the text of an article that says mobs of these ultra-fast robots doing the trading are actually operating at speeds beyond capability of humans, and so it's overwhelming the system. And so we're seeing things like crashes that take, you can see at the bottom, seconds, that is milliseconds, right? That tiny little dip is a crash, and the bottom is a spike. So price spikes and crashes that are imperceptible to humans because the amount of data that's going through and the speed is being managed by robots, which is causing market fluctuations that we're not able to control. They're calling it a jungle out there, and we need better controls and so forth. So real consequences, whether it's the NSA looking for terrorists or whether it's financial systems trading. All right, so ready for some robotic hugs, right? Danger. I wouldn't be anywhere close to those guys. All right, so that's basically the first half of the presentation, and now I'll, after I think given the context of the risk around big data, go into how it's being operated. And unfortunately I don't have a ton of time, so I'll go fast through some of the complicated sections, but I just want to give you a sense of how IT is in this transformation. We talk about this at EMC all the time. So we went from mobile, virtual, cloud, now we're in big IT. So this is a normal trend. We should just accept it and get on with it. And so one of the things that's happening is a ton of stuff is springing up, tons of technologies, and I'm going to talk primarily about Hadoop in the upper left-hand corner. I'm getting a presentation next week about machine learning on the right, which is another area of interest for me. But basically there are a lot of different levels. The three are, you have a lot of data that's coming in, you have a lot of analytics you do on the data, and then you have a lot of insights you try to make using a lot of the tools for big data. And Hadoop really has become the foundation, so we're going to talk about that now. What happens is we build this ultra-fast architecture to do the sort of cool things we think we need to do with the 3 Vs, and we tend to have our nodes distributed out. We share all the data to make it fast. We open up the access controls. We open up the networks. The clients are unauthenticated, and the web services are open. So it's an awesome environment, you know, for security. It's just like make it as fast as possible. But the problem with that is, you know, we really want things to be controlled because, as you saw on the start of the presentation, all sorts of bad things can happen. So the 3 parts of Hadoop are really your clients, your masters, and servers. So you think, okay, we'll just throw back some security on top of that. We'll just control these guys. And here I've tried to describe what they do. And if you're like me, quickly you read a lot of text, you go, I don't understand. Why are clients different than masters? What are slaves to masters? So let me try to put it in a different way using a graphic. Basically, we'll split it out. So you have clients on top, and they're making requests of masters and slaves. So the masters are basically doing sort of the control of all the nodes, because you'll have tens and tens of thousands of nodes in theory. You can run these labs at home with like 2 or 3 or 5 nodes, but they scale up very large. And then the slaves, you know, are sitting there and waiting for the masters to sort of tell them what to do. That's your basic architecture. And so you have job trackers that are talking to task tracker on every node, and then you have your name nodes talking to every data node on every tracker. In other words, you have data being deposited, and then you have stuff being done to it. That's it in a nutshell. So Hadoop is just a way of sending out data for compute. All right, so one of the cool things that's happening is, especially at EMC, we have products, which I won't talk to you about, but they take care of the availability problems. Because if you take that architecture and you put it onto these giant like storage arrays and you make it automated, it's hardware based. It's not virtualization, because virtualization slows things down. Why would you put a hypervisor in between? It just, you know, if you're just going to have all these identical nodes. So right now we're at sort of the physical layer, but if you build 10,000 nodes, you can basically do everything in RAID-like availability. If you look at this diagram, it should look familiar. If you're familiar with RAID, you're just basically striping all your data across all your nodes. And eventually, at some point, you get huge amounts of availability. You also get elasticity and scalability. So we can sort of take that off the table in terms of security. Here's actually, however, where Google started this in MapReduce in 2004. I called this guy who wrote MapReduce, and I said, hey, I'm writing a book about security. I really want to talk to you about the problems with security. Is there anything you want to talk to me about MapReduce and how it works? Do you want to work on it? That'd be awesome. And he's like, I know nothing about security. It's like, okay, wait a minute. You wrote MapReduce. You surely want to talk about how, you know, there's security needs. And he's like, no, I don't do that. I just do MapReduce. It's fast, you know, performance. Security guys are in a different department. Call them. You know, it was like weird. It was like bureaucratic. So I was like, okay. So in 2004, here is his idea for how, which I sort of explained to you in basic diagram before. But here's what I want to point out. In today's world, this is how MapReduce works. It really hasn't changed. And 2004 was 10 years ago, basically. So over 10 years, you know, we complain a lot about how firewalls haven't changed, SSL hasn't changed, but they at least are secure. Whereas when you get into MapReduce, there's nothing. So I started looking at it and I started to like draw little targets around, well, where would I secure things, right? So you have inputs, you have JSON communicating between where your data is coming in and where it's being accepted. You have RPC reads for it to be pulled down to do jobs on. You have output files, and across all of this, there are opportunities for attack. Your threat modeling can be very, very fun. All right. So, and then here's a quick animation I did because I had too much time on one airplane flight. And so basically, you can see that if you take your input and then you try to map it, the map sends it to all the nodes. The nodes then work on it, and they send it back to the temp file. Then the temp file gets picked up. This is the RPC read where it says, okay, let's reduce that, so it goes back to your different nodes to be reduced after it's been mapped, and then finally it's output. And so if you follow this process, it's basically, I'm going to send some data in, it's going to be pulled up, dropped on a local file source, and then put back onto the central, and then put back onto the local, and then put, so residue, right? You get data flying out to these nodes, being left in local storage. So forensic-wise, if you've done a lot of digital forensics, you might ask, well, what if I steal some nodes? What if I go in and pack up a rack and put it on a trailer and drive off with it? What am I getting? Like pieces of data that are meaningless because they're such shards, or am I getting like a whole set of data because there's 1,000 nodes within a rack? So, and there's residue on the HDFS is essentially a shared file storage. So there's residue in a temp directory, there's residue in places. Is that ever scavenged, cleaned up? So you can see where I'm going in terms of traditional security. There are a lot of questions. So this is the moment of reflection. Wow, where are we then really? A lot of people ask me about perimeters, and in particular because I'm an advocate for the keeping of perimeters. A lot of people say perimeters are dead, we're moving to this new world, mobile space, get rid of all the perimeters, but I'm a big believer in perimeters. And it's not because I think castles are cool. It's true, I do think castles are cool. But I think it's because overall we still have perimeters, like this room, even this door is open, that door is open. We have badges, so you can't get in unless you wear the DerbyCon badge. And those are perimeters that we use today that are modern and cheap and inexpensive, and that's the future for all of our tech. So MapReduce should work in a world where we can build really inexpensive perimeters, because our old perimeters may have been castle-like and expensive and very difficult to build. They might have lasted forever as well, but our new perimeters will be much less expensive, so we can throw them onto those little devices. So that's, whenever I reflect on perimeters I think old perimeters, those are expensive. Whenever I see a new perimeter, they're pretty flimsy and cheap, and that's where we're going. So how do you make flimsy and cheap perimeters becomes the security question for this new environment. All right, so perimeters are shrinking. They're obviously going away. We're getting rid of them, and I'm a big part of that at EMC. We're destroying perimeters to make you faster and more agile. We can actually move data 100 kilometers now to a different data center invisibly. You can write to two databases in two different physical locations. Well, what does that mean? Physical no longer is a barrier, so that's kind of awesome. Security-wise, there's a lot of problems you have to deal with. So the traditional data center goes away. We get this new modern data center. We move everything onto it. Now we're in this cloud compute space that's destroyed all the perimeters, and we have mobile people coming in from all over the world, don't even know what those networks are. So let's look at this new environment in terms of the people, the data flow, and the transactions they're making. And so really what we're talking about is transaction-based perimeters. So in the big data space, we're going to link our perimeters to identities. In other words, how do you really know, goes back to the beginning, right? How do you really know who somebody is? There's a study being done, it's kind of interesting, about how do you know whether a Twitter handle is male or female? Which by itself is interesting, because what if they're both? What if androgynous? But they're doing it in terms of male-female, so they're writing algorithms to go through and figure out if a person talks about this, they're male. If a person says that, they're female, right? Or there's the example of where Walmart started sending this woman pregnancy efforts and stuff like, hey, would you like to have help with your pregnancy, before she knew she was pregnant, right? So it was Target, Walmart. Yeah, the father got upset about it. That's right. Yeah, father. You want a drink ticket? It's like, that's worth a drink ticket. So I've actually drawn back from the philosophical past here a little bit. So anybody heard of analytic and synthetic attributes? Anybody? Can anybody name the person who used to talk about analytic and synthetic attributes? I'll give you a hint. It was German. So this is the English translation. Can anybody name a German? Freud? No. Jung? No. Hitler? No. Einstein? No. It was Kant. So if you can't name Kant. Yeah, so analytic and synthetic attributes were basically his way of saying there are things that are known, and then there are things that are assigned. So there are things that are absolute, and there are things that are just sort of assigned to things. So the attribute of root, for example, is like root is root, but then we might assign some group to it as well that it has powers of, even though it's always going to be root level. Or you can add groups to people. So they have lots of different attributes they gain, but they're still intrinsically that one user. So philosophically, we have a long heritage of understanding how to do this, which I think is going to start being applied to big data environments. More and more of the social science is creeping into computer science because it's more about human behavior, it's about deep philosophical, identity, metaphysical questions. But for the time being, we're using computer science to solve a lot of these problems, and so those are just simple factors like locations, the devices you're on, the activities you're doing. So for example, if your company has a record that you bought a plane ticket to Spain, when you log in from Spain, they know that you bought a ticket, so they can say that's you coming into our network. They can also say that, you're moving very quickly on GPS, so that's cool, they know you're driving, whereas if you're moving from Argentina to New Zealand, that's too fast. That's obviously two people coming in as opposed to one person moving. So, and you can also have policies where you keep lists of behavior and then go back and say, does this match the behavior that we've seen before? So this is how we're sort of linking to identities. And that's because identities are really important, but if we link them to identity as a database, then people steal that database, as you'll see in a second. So we'll start with passwords. The problem with passwords is they're kind of stupid and people steal them. Interesting data I've noticed here is that if you try to link behavior to secrets, like we know you're you because of this secret, then we'll basically find 98.8% of all users are using the same 10,000 passwords, whereas 2.3 million passwords are being used by just 0.18% of all the users. So a lot of secrets are being stolen. The ones that are being stolen are the ones for the users who are trying to be unique, and that defeats the last 1.8%. We've already defeated the 98.8% because they're the same. We have a very short list, and then we defeat the last bit, which is so small, by just going and stealing a database. That's why it's so important to steal databases. So I don't know how many people saw that Brian Krebs story recently on how all the identities have been stolen, right, as a service. So it doesn't really make sense to use a huge database. No matter how big the data is, the data set, if someone can just walk in and steal the data set, then it's not really a secret, so it's not really your identity anymore, it's someone else's identity. However, behavior now becomes way more important because that's something you can't necessarily steal because it's changing. So it's a prediction, it's like things that are much more dynamic. So this is why I say it's a new approach. And this actually takes me back to a time when I went to a CEO of a trading company, very, very powerful, huge amounts of money, and I said, aren't you really worried about somebody stealing our secrets? And he was like, no, actually, because no one can do what we do. So it wasn't actually having the data that we had that made us useful, it was the intelligence we had about how we approach things. So this new approach takes all this data and tells us ways to find things, find meaning in that data. So I talked about this in 2011 in terms of the snow map. In 1853, we figured out how to find cholera by looking for behavior, and the behavior told us where there was an infection. So we can actually do sort of like different levels of awareness and different levels of testing to figure out, this is actually a real test, by sample interactions, with over 50 million transactions a month, we were able to review just one of every 2,000 transactions and still detect 92% of fraud. So it was pretty cool. And if you think about that in terms of flights, if they just sampled one of every 2,000 passengers, it would be way easier to fly, right? They're sampling like every single passenger. So this is sort of the thing we're doing because at scale, we just couldn't keep up. At 40,000 nodes, there's no way to keep up. We need nodes to really be able to see other nodes and know they're poisonous. So this is the ghost map done in an awesome 3D version. I just found this. One thing I like to point out over and over again is there's a little white space up at the top right. I'll highlight it here. Anybody remember why that's white? Why nobody died in that space? The red lines indicate the number of deaths. Is over a well? Different water sources. Well, all the blue flags are different water sources. They're pumps. Any guesses why? Brewery, that's right. Who said the brewery? All right, drink ticket. That definitely deserves a drink ticket. Oh, so close. We can come get a couple after. All right, so the brewery basically had its own water supply, which is, and they drank a lot of beer, so they were saved. But the map here basically shows that you can walk to the pump, and the distance you're away from the pump is basically the likelihood you'll die. The further you walk, the more likely you'll go to a different pump and you'll survive. All right, so the modern ghost map, we actually built this flight simulation at EMC Worlds, and it's a 3D visualization. It was a huge dome, and you could actually sit there and take you through. So this is a visualization we built of the future of threat mapping, the future ghost map. And so we started to notice studies done after my talk in 2011 where people started to apply that concept. Before 2011, I did not find a single person talking about the ghost map other than Edward Tufte and other people about visualizations, but no one applied it to network security. So after I spoke about it, for some reason, it just started popping up in all these universities. And this is the latest one I saw from West Point. The United States military figured out if they can take 5.6 million nodes and 28 million edges, they can find a seed set of social influence in under 4 hours. So which means they can find social influencers almost, immediately. They can turn on an engine, they can find out who's starting a terrorist network or who's starting a discussion around bombs and so forth. All right, so let's talk about solutions. I have a few minutes left, so Let's talk about hugs. All right, this is a true story about a dog that actually became friends with a polar bear in the wild. Polar bear came up to a bunch of sled dogs and started like playing with them. The sled dog owner was like, oh my God, he's going to eat all my dogs, but he really just wanted hugs. You'd think it would be dangerous. All right, so the future directions of big data really are that we're doing at least three, probably more things, but let's boil them down to acquiring data, we're storing data, and we're querying data. And there's lots of cool tools, and they keep populating. It's like they just spring up. Drill just came out. Drill was just approved. Drill allows you to do ad hoc queries of data. That's why it's called Drill, I guess. And so it's kind of scary. The first thing I thought was, oh my God, you can go in and pull data from almost anywhere, and you can do like analysis of it, and it's going to be crazy. And I went in to look at the security. No security so far. I haven't found anything yet that talks about how to protect people from doing drills in your data. So the bottom line is, the model for Hadoop still is like create that castle, a very expensive perimeter, and make sure no one gets in or out of it. And we're moving to a world where everybody's going to want to drill through your perimeter. So if you're using drill and you can't build very expensive perimeters, what are you going to do to protect your data? All right, so the way we're doing it is in the acquire space, right, you want to do things like data validation. Obviously, SQL injection is the perfect example of this. If you're not protecting the data coming in, you're not going to get good data. There's also ways of doing aggregation. So remember data scientists saying, hey, don't put your data in here, we might do bad things with it. Well, you can sort of aggregate it, so instead of the actual date of birth, you would take the group that you're in. So these people are in this age group, and these people are in those age groups. Now you don't have date of birth anymore. You can add salts, these are actually statistical methods of protecting data. You can imitate data using synthetic data. You can replace data. So in your acquisition phase, you could actually specify that the acquisition has to be safe because it's going to use these methods. Another thing to look at is how you store. This is where EMC obviously specializes, but we can look at better encryption. We can look at enforcing RBAC, so role-based access. You can look at authenticating APIs. It's pretty hard, but the idea is if someone's going to access, they need to have authentication before they do. You can harden clusters. I've seen no research on this. You want to get involved? Work on hardening clusters. That would be awesome, which is just basically a hardening list for people who deploy these things. Logs. To be fair, there are companies that are advertising security for Hadoop, but it's pretty much snakeware at this point, or snake oil. So you've got logs, very difficult, almost impossible to do log analysis, and then forensics, as I mentioned. And then on the query side, you actually have data queries that people are pulling data out where you can, again, do unique users with RBAC. You can restrict the amount of load they can put on your systems because you can create denial of service situations. Basically, you can see this is all business logic. There's some of it's technology, but most of it is people are going to abuse the way that they access the data or create the data. So there's a huge opportunity for security now in big data. We really need more research and more people working on it. And like I said, I called the MapReduce guy. He did this 10 years ago, and since then we're still where we were, and he said, I don't do security. So it's like he's handing it to us on a silver platter, like do something with this. So we really need to get on it. All right, so one of the things I can recommend is you can create a compliance checklist. And so everybody loves compliance. But these are real checks you can do now. The first is you can do some node access restrictions using authentication. You can use Kerberos, it's pretty painful, no one likes it, but you can do lots of stuff with authentication that's at least at a level beyond the base. You can start to do data disk encryption. There's some good companies out there that are working on ways that the nodes themselves will have the data encrypted, so if somebody walks off with a rack or an array, there's a chance that they won't be able to get the data if they can't find the keys, key management being the operative issue. You can do some API authentication, like I mentioned. The bottom three are interesting because a lot of the controls in the environments you'll see assume that no one has root. They assume that there's no man-in-the-middle opportunity. Again, it goes back to the perimeter. I don't think these are fair assumptions, right? Because if everyone in your company is looking at this data and saying, wow, I can do great things with this data, then you really have to ensure that they're not going to get root. So finally, logs. You can try to do logs, but look at this line at the bottom. Anybody know what this does? It's sudo -u HDFS Hadoop FS minus RMR. That's right, it deletes all of your data. And HDFS is the root in Hadoop. And basically, you don't have to actually authenticate to do this. You would just be in the environment, create a node, and then, because it's like old Unix, if you remember, right, remote scripts, remote copy, R shell, you just say, hey, I'm HDFS, and I want to delete the entire thing. RMR is basically RM minus recursive. They've just shortened it to RMR. So pretty cool. You can go in and delete an entire data set. if you think about that, it's okay, that's a lot of data, but the amount of time it takes to move data sets is fairly significant. So if it takes you like 60 hours and Amazon's charging you for the amount of time it takes you to do processing and stuff and moving stuff, then you can force people to start over and move all that data back in that environment. That's a major financial impact to an organization. Removes all the performance benefits they just got out of that Hadoop cluster. You can continuously keep them from getting any performance out of that environment. So the CSA has some guidelines. I find them to be pretty sparse. On the left, they say this is the old way. On the right, they say this is the new way. And you can see NoSQL has very little security in it so far. I say Squirrel because there's actually a company called Squirrel. And so I'll wrap it up here. Basically, Squirrel and NoSQL have some controls that we're beginning to develop. It's probably the most advanced, and I'll tell you briefly why it's the most advanced. It's HBase, which was the NoSQL database of Apache, but with controls. And the reason is because in 2006, Google came out with Bigtable. In 2008, the NSA noticed this and decided they'd start working on their version of it. So you might take some wild guesses why the NSA thought they needed to protect big data. And so they, in 2011, were kind enough to release to the public this thing called Accumulo. And Squirrel is actually some ex-NSA guys who are now running this and working on this as a private version of Accumulo. It's probably too small to see, but if you look very carefully, you can see that you can actually create authorizations. This is the code that you would use to create authorizations for the code in big data. And here you can say, you know, Alexander has different permissions than Snowden, and you can say when you scan to get the values, you're only allowed to get the things that you have access to. So this is the very, very beginning. This is the most sophisticated example we have so far, I would say, of how you can control big data. And so it's really easy too. You can see, you just create, you get on one of these groups, you join the Apache groups, and you start saying, hey, let's make Hadoop more secure. Code reviews, I'm already working on Hadoop code reviews to get rid of some of the issues in the code. So lots of opportunities, but this is one of the best examples in big data security. So long term, basically just realize that everything has to change. It really does. Unlike virtualization, I felt like we were making incremental progress and we could really handle it. It was easy to secure virtualization. It's not easy to secure big data. We really have to take it as a new approach and really focus on where your assets are so you can understand the best way to be a boss. Work on big data, operations, security, and solutions. So thank you for your time. I hope that was useful, and come see me if you want drink tickets. Yes, are there any questions? I could answer those too.